The concepts and radio. So these are the topics which I am going to cover it up. The traffic direction, bidirectional transport modes, radio medium sharing modes, then antenna basics, which will cover up the directivity, radiation patterns, MIMO techniques, and comp. So these are the full topics which we are going to cover up in the full slides. So what are the basic technologies? Uplink and downlink. Uplink means UE to the base station, and downlink means the base station to the UE. Now we have two kinds of transmission modes. One is half duplex, the another is full duplex. The half duplex means the nodes can transmit and receive simultaneously, which is common for both half duplex as well as full duplex. The main difference is half duplex base station can communicate with only half duplex UE, whereas the full duplex base station can support both the half duplex as well as the full duplex UE. Now coming to the radio medium sharing modes. There are two kinds of modes. One is FDD and another is TDD. So FDD is nothing but frequency division duplexing. TDD is nothing but time division duplexing. So the FDD is nothing but the uplink traffic occurs in one frequency and the downlink traffic occurs in the another frequency. So basically in FDD, the frequencies are different in case of a downlink as well as an uplink direction. This is the main difference between an FDD and TDD systems. In FDD, it supports both half duplex as well as the full duplex modes of operations, as well as efficient for symmetric traffic, means similar data patterns are observed in DL and UL. That is called FDD. What comes in TDD? In TDD, uplink and downlink frequencies occur on the same frequencies. I mean, the frequencies in the downlink and the frequencies in the uplink are same in case of a TDD systems. It supports only half duplex modes of half duplex operation of the nodes. Third is efficient for asymmetric traffic. Here you will see the downlink traffics are significantly higher than the uplink traffic. That is what we call as the TDD mode of operations or TDD systems. FDD systems, you will find the similar amount of data in the DL as well as in the UL. Now coming to the basics of antenna technologies. So we have called wavelength C into speed of light divided by frequency. If the frequency is 2.4 gigahertz, your wavelength will be 12.5 centimeter. If frequency is 700 megahertz, your lambda will be 43 centimeter. With the help of the formula, this lambda value is calculated and it is being shown. So what do you mean by radio antenna? A structure associated with the region or transition between a guided wave and a free space wave, or vice versa. It radiates energy. I mean, you see there is a transmission line and a generator. A transmission line is nothing but the spacing between the wires is only a fraction of the wavelength. An antenna is nothing but the separation between the wires in the range of one or more of the wavelength. So between the wires and the wavelength, the antennas are being separated by distance. So that distance is called as the wavelength, and wavelength is calculated using C multiplied by speed of light divided by frequency. So there are different kind of antennas. One is isotropic antenna and another is non-isotropic antenna. So isotropic antenna, which is called as the energy fed into the isotropic antenna, is radiated in all directions equally over the surface of the air. Whereas in case of a non-isotropic antenna, the energy fed from a non-isotropic antenna is radiated only in some directions, only a part of the surface of the sphere. Where in case of an isotropic antenna, it is radiated across all the directions equally over the surface of the sphere, whereas in case of a non-directional antenna, non-isotropic antenna, it is radiated only in some directions. So that is the difference, and how they are calculated. They are calculated using the formulas which is being written below. Now coming to the non-isotropic antenna. Non-isotropic antennas are characterized by the capabilities to focus on the transmitted energies. So this is like how the antenna gain is calculated. Surface radiated by an isotropic antenna divided by the surface gain by a non-isotropic antenna. So that is called as antenna gain. So when expressed in dB, that is equal to 10 log SI by SN. SI is nothing but isotropic antenna and SN is called as a non-isotropic antenna. So that is what the difference between your directivity and gain of an isotropic antenna as well as non-isotropic antenna. So antenna gain is calculated as SI divided by SN, isotropic antenna divided by non-isotropic antenna. Now coming to the equivalent isotropic antenna and non-isotropic antenna. So you see the generators are being pushed out from the left to right in case of an equivalent isotropic antenna. So these are basic differences where we can see it between an isotropic antenna and a non-isotropic antenna equivalent. These are the basics RF terminologies. This is another equivalent isotropic antenna where del PTM is equal to PT into GT divided by 4 pi R square. So these are different kind of formulas of the directivity or the gain which is being calculated using directivity of the isotropic antenna. This is called free space path loss where the receiving antenna aperture is calculated is equal to AR equal to GT multiplied by lambda square divided by 4 pi. If you want to go in detail in distribution, you can see the amount of energy integrated by the receiving antenna is equal to PT multiplied by GT multiplied by GR divided by 4 pi RF by C whole square. So this is if you can go deep down into the details where you can find out the free space path loss, how it is being calculated. It is more into the RF side of 5G network. This is what is being required, is you have to go through the basics and try to understand the different terminologies and aspects with respect to the free space path loss, how this loss is being calculated. Now coming to the power received by the RX antenna. So sometimes we have TX antennas and RX antennas in our base stations. So how to calculate the power received in that RX antenna? PR dBm is equal to PT dBm plus GT dBi minus path loss plus GR dBi. So these are nothing but there are different kind of what you can say. PT is power transmitted or injected into the transmitted antenna. PR is nothing but power received by the receiving antenna. GT is called as the gain of the transmitting antenna. GR is called as the gain of the receiving antenna. R is called as the sphere of the radius, that is distance from the TX antenna. F is radio signal frequency and C is called the speed of light. How this is being calculated? This is calculated by using the logarithm formula of the power which is being received at the antenna. So basically antenna gain, transmit and receive is a function of the direction. If the directions covered by the antenna is equal to the increase in energy density relative to the isotropic antenna is not in same as all the directions covered by the transmitting antenna. These are called as nothing but the radiation patterns. How the radiation patterns are being developed, we will going to see. So what are the different kind of radiation patterns? One is omnidirectional antenna and which is again of different types. One is 2 dBi, another is 6 dBi. These are called the gain of the dBi pattern. One is plus or minus 60 degree, the second is plus or minus 10 degree. So first the direction horizontal and vertical. One horizontal is plus or minus 180 degree, the second is also plus or minus 180 degree. The difference is the gain. The gain of the antennas are different in case of an omnidirectional antennas. First is the 2 dBi gain, the second is the 6 dBi gain. So now coming unidirectional antennas. Unidirectional antennas is again of two types. One is 8.5 dBi, another is 12 dBi. The difference is horizontal as well as the vertical path. The horizontal is plus 37, the second is plus 11. You can see the size of the radiation patterns, how the radiation patterns are triggered from one end to the other end, so that the signals are distributed across the regions. So these are radiation patterns. Again now comes to the sectorial. So this is something like some sectors are being divided into with a different kind of antenna gain. One is 17 dBi, another is 12 dBi. So with kind of an horizontal as well as the vertical. So horizontally it will transmit 32.5 degree with a plus minus a vertical degree of plus or minus 3.6, the first one. The second one is of a sectorial which is 12 dBi, which is again plus minus 31.5 degree with plus or minus 10.5 as a vertical elevations. So these are different kind of radiation patterns which are being there in the antenna basics. So these are horizontal patterns and the vertical patterns in the gain. If you enter the gain like 2.5 dB and front to back ratio with 1 dB, you will get the horizontal pattern and the vertical pattern of the antennas. So what we call is the radiation patterns. Different kind of radiation patterns are there. You see here the gain is 18 dBi, front to back ratio is 30.56 dBi. You see the calculations how it is being calculated, and it is throwing in horizontal pattern and a vertical pattern of those antennas. This is another example with 24 dBi and 36.7 dBm. So this is single patch antenna and the multiple patch antennas. So again, the single patch antenna is having lesser gain, which is 9 dBi, and the multiple patch antennas, it is 18 dBi. So again, we are having horizontal as well as the vertical. So horizontal means the straight line and the vertical means the opposite line of the antennas. You can able to see how the single patch and multiple patch antennas are being covered up. So this covers my first topic. Going ahead, we will talk about MIMOs.